We've talked now about potential, the idea of potential. Let's actually calculate it. Let's calculate the potential near a point charge. And just to save me a lot of time and a lot of chalk and a lot of breath, from now on, the rest of the class, when I say potential, I mean the electric potential. I'm not going to say electric every time anymore. If I mean energy, I'll say potential energy. But if I just mean electric potential, I'm just going to call it potential. So there it is, just the potential. Okay? So we're going to start with a point charge, or we might say a sphere of charge. We can call it a sphere of charge plus Q. And have field lines coming out like this. Like that, and more field lines I like to draw like that. And let's think about the potential of a charge as it moves from point A to point B. Okay? So we're going from A to B. And first we want to calculate the change in potential energy. Okay? Change in potential energy. We'll get to the potential in a minute. But first, the change in potential energy. So potential energy we usually label as delta U, and you have to be very specific about the 2 points. So we're going to talk about delta U if we took a little charge, a little test charge plus Q, from A to B. And even that is difficult when you think about energy. And one way to prove that is when I teach this class, and I have 300 of these brilliant little Rice freshman minds in here, I ask them the following very simple question. I walk into a coffee shop with $10, and I walk out with a cup of coffee and $8. What's the difference in my money? So here, you just shout out, what is the difference in my money? Walk in with 10, walk out with 8. And I bet you, if you're like all these brilliant Rice minds here, you said $2. And that's wrong, okay? You lost $2. The difference in your money is negative $2, if we're going to be technical, okay? So in the mathematical world, difference is always the final minus the initial, always, okay? So if I went from $10, if my final was $8, my initial was $10, it's minus $2. So you got to be careful with negative signs when you do changes in energy and changes in potential. Now, when we speak in language, we often have words that account for the negative sign. I went to the coffee shop and I lost $2. Well, the lost implies the negative sign. I blew $2, you know, et cetera. Blew means you exploded the $2. So all these numbers, all these words can give you the negative sign. But in physics, we can't just use a word. We have to actually make sure we have it right. So a difference is always final minus initial, okay? Let's see. So what is that energy going to be? If we go from here to here, if we just have the test charge here and just let it go, it's going to feel a force pushing it that way. It's going to naturally just fly from here to here. So in this sort of work and energy stuff, you got to think about the system, right? There's external and internal, all that. I'm not going to review that in great detail. But here, the system is the charge and the big charge and the little test charge and the fields they create, okay? So the system is doing the work. As the charge flies from here to here, the force is due to the system. So this is what's called internal work. The system does the work. When the system does the work, it's negative. The change in potential is negative work internal. Because if the system does this work, it's giving up some of its potential energy to do the work, right? That's why the change in potential is negative. It's losing some energy for the work that it does. So that one is negative W INT. So we calculate this work, and what is it? Well, we bring the negative along, and work is the integral from A to B of F dot ds. You might think of work as just F times X, but when you're really doing integrals and things are changing, it's the integral of F dot ds. So there's no inherent negative sign on this integral. Work is this integral, and I'm carrying the negative along. So then we just have to say, well, what's the force? The force is just the charge Q times the big field E. So we write it one more time. It's equal to the negative integral from A to B of the test charge Q E dot ds. And remember, the little ds's are the little steps we're taking as we go from A to B. There's your little ds. So you can look at this and decide if this looks right. So we aren't doing potential yet. We're still on energy. But we're saying that the energy should come out what? It should come out negative. We're losing energy. We're going from here. We're gaining a lot of kinetics, so we must be losing energy. So this thing should come out negative. It's got a negative sign there. That's a good sign. Will the integral come out positive? Yes. The charge is positive. The E field has a positive magnitude, and so does the ds. And they're in the same direction. Right? E and ds are together. So this integral is going to come out positive. There's a negative sign there. Therefore, the change in energy is negative. Everything's fine.